Hey gang, welcome back to class. Today we're going to finish up our semester's review, get us caught up to all the material we've covered so far, so that next week we can start some new material and move on forward. Alright, let's start with a prayer. Dear Father, thank you for bringing us back together again. Thank you for keeping us safe. Thank you for giving us this desire to learn and the continuance of our school, even in harsh circumstances. Help us to hold firm in this crisis and grow. Help us all to be healthy and happy and strong, and bring us home back together again in the future. In Jesus' name we always pray. Amen. All right, so I'd like to start off with a little bit of this wave discussion. We're talking about the superpositioning of waves. So that's when just two different waves kind of line up on top of each other. Once they get on top of each other, they start interfering with each other. So as these waves are going up and down and up and down, they're bumping into each other, reinforcing, making it bigger, or canceling each other out, making it smaller. As these waves are both moving, when the trough, the bottom of the wave, comes into contact with the crest of a different wave, the top of the wave, they cancel each other out. So they get to that zero, that null set. That's cancellation. And then on the other hand, if a crest lines up with another crest, then they're going to reinforce each other. And instead of being two waves, they're one wave that's twice as big. Twice the amplitude, twice the amount of energy involved in the wave at that point. Now I've got a problem with all these waves bouncing in and out and on top of each other. They don't just flat on the screen here. It's harder for me to draw these waves in 3 dimensions, so I got to draw them the way I got to draw them. But we're talking about 3-dimensional life. All these waves are moving every direction, all along the other 3 axes. The interference patterns that we're talking about, this cancellation and reinforcement, they only interfere with other waves when the waves line up. Only with the portions of that wave that line up along these given axes. If the X and the X line up, the X may interfere, but the Y and Z, not so much. So you see these different waves as they're going flat or they're going straight. They're interfering with each other in different directions, all over the place. Next idea we'll talk about is excitation. So where do these waves come from? So as we're adding energy to our atoms, the electrons will go from one shell to the next shell and excite up to the topmost shell, and so on and so on. And eventually, if enough energy is added to that atom, this electron gets ejected completely and travels out as energy. Or, on the other hand, if it doesn't have enough energy to eject the electron completely from the atom, it'll drop back down. So when it drops back down, that gives off energy. And all of these different energies are coming off in the form of electrons, in the form of base energy, and they're being ejected from this atom by the electrons moving up and down. Each level, each sphere of this shape atom has a certain energy associated with it. As it moves up, it has a certain amount of energy that must be ejected in order to move from one to the next. These come out as electromagnetic spectrum. Light waves. As we know, there's 3 variables for every light wave there is. Everything along the electromagnetic spectrum is defined by 3 separate variables, whether it's the frequency, how often it hits you, the amplitude, the height, the amount of energy, or the wavelength, the length between the waves. All of these different waves coming off of these atoms being ejected in every direction, all defined by those 3 separate variables. Whether they're being absorbed by a substance, when light hits it, does the material absorb the light so that it only looks one color, one portion of the electromagnetic spectrum? Or is this thing glowing so that it's emitting light, giving it off All of these are just different waves, different bands of the electromagnetic spectrum. Finally, let's talk about these waves a little bit more. Sometimes they look like they're particles. These electrons flying through the air, these individual things hitting a solar cell, for example, and these solar cells are converting these electrons flying through the air into electricity that lights the light bulb. And these particles move along this wire. As these moving electrons are flying through the air, they're manifesting as what we know as photons, a collection of energy that happens to be a particle. So we got a photon, which is an electron in motion. This energy projection as in moving. Sometimes these things, they look like they're waves. As we were talking about diffusion before, these waves are going out. So how can this electron, this thing, come out and do this? Well, sometimes it's a little confusing. A good way to think about that, so we can understand the wave-particle duality, is this electricity and magnetism. Both of them are associated with moving electrons. This electric current's moving in a straight line, kind of looking like a particle. And then we have our magnetism, these spinning electrons, still moving electrons, these spinning electrons creating this field of energy. This magnetism. It's not a direct correlation, but it's something to help you understand the complementarity of these different particle and wave nature of energy. Uncertainty. The last thing I wanted to talk about was uncertainty. You hear a lot in science fiction movies about, well, sometimes it could be one way or the other, and we don't know. The best way to think of it is being both at the same time. Well, that's uncertainty. It's not a case that it is both at the same time. It is only one or the other. That electron is somewhere. It is a thing that exists somewhere. The problem comes in when we're looking at that. We're trying to observe and figure out where it is. When we look at it, we're looking using light, using electromagnetic waves, using energy of our own that is interfering with the motion of the electron we're trying to find. So we don't know whether or not it's the electron's motion we're observing, or is it because we have included energy of our own to that electron and made it move in a different way, changing those three variables. This difference between what it would be and what it could be is called uncertainty, or Planck's constant. A man named Planck came up with this observation. 6.6 times 10 to the negative 39 joules per... Wow, that's an unusual number. Where did we come up with it? We observed the world and described what we saw. It has no other significance other than that's the number we needed to make it work. As these different numbers come across, we insert ourselves into the process to help us understand what's happening. We're not defining things, we're describing things. As we look and observe, we describe what we see. That is science. Planck's constant will come into play again, and you'll need to remember this idea as we move into chapter 32 next week. With that, thanks for coming, and I appreciate your time, and I'll see you next week. Have a great day.